All right, so this is number 2 from your review. Okay, the first part on page 192. And it's still falling under what they kind of deemed as being reciprocal linear functions, right? And so if that's a bit of a jumble for you, it just simply means 1 over x or variance of it, okay? And typically these graphs, you can see that the degree of the denominator is larger than the numerator, and as such you would have y equals 0 as your horizontal asymptote. Okay, so the other piece to this is that we've got a vertical asymptote, and in part A, I can see that that vertical asymptote happens at x equals 1. And so what we're going to say is the graph is never going to equal x equals, the graph is never going to be able to get to x equals 1, right? Because the vertical asymptote, and so you're going to say x can't be positive 1, okay? And then subsequently x minus 1 can't be 0, right? So all I did there was minus 1 kind of thing. This is the piece that's going to end up in your denominator. So what we're going to say though is it's something like this, okay? Now the catch here is though I can't necessarily definitively say that that is going to be 1 all the time, okay? And so what I'm going to actually do is not call it 1 for a moment. I mean, maybe like a, right? Like is there a vertical stretch or compression of these linear graphs? Okay, and that's what we're going to find out. We're going to actually solve for A, or compression. Okay, so to do that, you're just going to identify a point off of your graph. Like I may use, and a nice one, mind you, right? Like, I don't know, might use the y-intercept there. Okay, and so what I can do is I'm going to have a point, 0 and -2. And so I can actually go, well, what happens if I have 0, right? For 0 for x, that means the function is going to equal -2. So I can actually go -2 is going to equal a divided by 0 minus 1. Okay, and so I get -2 is going to equal a by -1, and then I can multiply both sides by -1. Okay, and we get a is equal to 2 here. Okay, just be careful. Like, you can't just assume that it's 1 over all the time. Okay, you can kind of tell after that we have seen now. So I can actually rewrite f of x as this. It's actually not 1 over x minus 1. It is 2 over x minus 1. Okay, so just be a little careful with that. It may be a little bit of a trick. Okay, I can kind of see that if the graph had not been vertically stretched, that point right there should have been right there. Okay, so just be a little careful. Like, it would have come down here and it would have been a little closer to the diagonal of the intersection of the vertical and horizontal asymptotes. But you can kind of see it has been vertically stretched a little bit. Okay, specifically by a factor of 2, which is the a value that you have now incorporated into the numerator. Okay, so for question B, we're going to do the same thing. It looks like I have an a vertical asymptote at x equals -4. Okay, and so I can say, well, x can't be -4, and so x plus 4 can't be 0. So there's the piece in your denominator. And again, we could write a by x minus 4, sorry, x plus 4. Okay, and then we're just going to try and solve for a, again, using a point off a graph. And so what I see, you can pick any point, really. Like, there's a couple available to you pretty nicely. There's one there. Okay, that's there's a point at -3 and 1. Okay, so 1 is going to equal a over -3 plus 4. Okay, and so we can just solve for a. We're going to get 1 is equal to a over 1, multiply both sides by 1, you're going to get a is equal to 1 in this question. So I guess the point here is just be a little bit careful, okay? I would say maybe just try and solve for a all the time if you're proposed one of these questions. So the equation is going to be, actually this time you got lucky with the 1 as there's been no vertical stretch or compression. But just be a little bit careful when you're tackling problems like this, and don't just assume that the numerator is always 1, okay? Not always 1. Okay, just be careful.